When we have an aromatic ring that already has a group attached to it, which we sometimes refer to as an original group, then that group will have effect both on where a new substituent is added, which is called the directing effect, as well as how fast the reaction goes, which is the relative rate of reaction. And this applies whether we have just one group or multiple groups. And we refer to directing effects by the relative position of the new substituent, which could be ortho, right next door, meta, or para to the original group. And we'll find that ortho and para are linked, and so that groups that direct to one will direct to both. And our question centers around about what type of director our group is, centers around whether or not it will stabilize the cyclohexadienyl carbocation intermediate. So we'll talk some about that. And essentially, when we look at any given group, we ask the question, does that original group or thing that's originally on the ring stabilize a carbocation? If the answer is yes, then we have an ortho-para activator. Unless it's a halogen, special case that's an ortho-para deactivator. If the answer is no, then our original group is a meta-directing deactivator. If we take a look at the nitration of toluene as an example, we know with the combination of nitric and sulfuric acids that we're going to replace one of the hydrogens on the toluene ring with a nitro group. And so our question of regiochemistry, or where that reaction happens, is going to be whether the nitro replaces the hydrogen that's ortho to the CH3, meta to the CH3, or para to the CH3. And these are our three possible constitutional isomers as products. And to figure this out, in short, what we do is ask the question, does the CH3 stabilize a carbocation? And if we think about that carbon on the ring having a positive charge, we look at the original group. Our point of reference that we're comparing it to would be a hydrogen. Take a moment and see what you think. Which of these two carbocations with the original group or with a hydrogen is more stable? The original group does stabilize a carbocation, in this case because it's tertiary instead of secondary. Remember, that's what we'll call an inductive effect. Specifically, that the CH3 can be electron donating through bonds and can share some of the electrons it has versus a hydrogen, which only has the electrons it actually shares with the carbocation carbon. Now let's take a quick look at the mechanism to see why this is important. Before we do, though, what this is going to tell us is that because we answer yes to that question, that the CH3 is going to direct that nitro preferentially to the ortho and para positions. So those two are going to be our major products. And that the meta nitro toluene is a minor product. It'll still be formed to some extent, but in lesser amounts than the ortho and the para. And to understand why, let's take a quick look at our mechanism And let's start with the mechanism for the addition, or substitution rather, at the ortho position. Take a few minutes here and see if you can draw this mechanism. And remember, the first step is going to be the breaking of one of the pi bonds to grab our nitro electrophile, nitronium ion electrophile. We've got to break one of the nitrogen oxygen bonds in the process. Let's make sure we draw in the carbons where that pi bond is breaking, and that we show that hydrogen on the carbon where the nitro group is going to substitute to. And what we find then is that we can add the nitro at that ortho position, and when we do so, the carbocation lands on the carbon with the original group. And remember, this is a stabilizing effect, because that methyl group can donate electron density inductively to the carbocation more so than a hydrogen. And then, of course, if we want to finish out our mechanism, we just need some base to come along, let's say water, that's formed when the nitric acid gets dehydrated. We pick up that hydrogen and we re-aromatize our ring, giving us our final product, in this case ortho nitrotoluene. And we'll also get H3O+, although it's not critical we write that. Now, the key intermediate that's going to tell us whether our original group is ortho para directing or meta directing depends on the stability of this key intermediate. And this intermediate we refer to as a cyclohexadienol carbocation intermediate, because we have a 6-membered ring, 2 double bonds, and this positive charge. And let's do a little practice here where we draw out additional resonance structures. Let's pause the video here if you want to and see if you can draw the additional resonance forms of the cyclohexadienol carbocation intermediate and the mechanism arrows that show how we get from one to the next. And remember, this is essentially like an allylic system in the sense that we have a carbocation adjacent to a carbon-carbon pi bond, which means we can relocate that double bond and move the charge to the other end of that 3-atom system. And we can do that with the other pi bond here in the ring as well, which means we'll have a total of 3 different resonance forms. Now, the one that we started with is actually a little bit better because it's more highly substituted. This one is tertiary, whereas these 2 carbocations are secondary. But the fact that we have resonance to get to the other ones makes that extra helpful. And if we think about a resonance hybrid, remember that we are looking at a structure where we have 1 carbon that's in the ring that's sp3 hybridized. The other 5 carbons are going to share those 2 pi bonds. Let's not forget our methyl. And then the atoms where the positive charge is on at least 1 structure have a partial positive. And so what we note here that is if we put the original group ortho, or there's the new substituent ortho to the original group, that the positive charge can go where the original group is, in addition to 2 other places on the ring. And if the original group can stabilize a carbocation, like a methyl group would, then that is a positive factor, and that favors that substitution. It makes that substitution go faster because that intermediate is more stable. Now, just as an exercise in visualizing why this helps, let's take the meta and para intermediates as well and do the same resonance practice with those. So if we had substituted either meta or para, this is what we would be seeing as our intermediates. Let's see if you can complete those alternate resonance forms and see if you can draw a resonance hybrid as well. Just to run through those quickly, we remember have the same flow of electrons that we do when we have the ortho substitution pattern. Notice that by moving the double bond over to where the carbocation is and then moving the carbocation to the other end of that 3-atom system, we've actually skipped over the carbon that has the methyl group. And if we complete the other structure, the positive charge is still further from that methyl group. And even in our resonance hybrid, what we observe is that that positive charge never ends up where the methyl group can help it. It's on every other carbon, skipping around where that methyl group is. And again, this would be our resonance hybrid. So there's no way for that CH3 to directly help the carbocation like it can in the ortho case. Now if we do the same trick with para, we'll find that there is a structure, this very next resonance form, where the positive charge can be where that methyl group is. So we do have a tertiary carbocation in the para case as well. And if we just complete our resonance practice, draw our hybrid, we'll see that again we have the positive charge on alternating carbons, but now we are also including the carbon that has the original group on it. And since the original group in this case can help stabilize a carbocation, the intermediate for ortho and para is a little bit more stable, a little bit lower energy, a little bit more accessible than that of the meta. And so the ortho and the para are favored. Again, because that original group can help stabilize that carbocation intermediate. Now let's just take a summary look at our 3 resonance hybrids for ortho, meta, and para substitution of toluene in a nitration reaction. These again are the cyclohexadienyl carbocation intermediates and the resonance hybrids of all 3 resonance structures of each. And notice that in ortho, we have a place where the positive charge can land on the carbon that bears the methyl group, and that's true of para as well, which makes them more stable, therefore better than the meta. So if that interaction, that original group, which in this case is a CH3, stabilizes that carbocation, we have an ortho para director. Because that reaction at that position goes faster than it would otherwise. Now let's imagine in contrast that we have the nitration of nitrobenzene. So we have for our original group a nitro, we're adding a second nitro. If we put that in the ortho position, then that positive charge can land where the nitro is, the original nitro. If we go meta, then we unfortunately, well, for better and for worse, don't have that charge end up where the original nitro group was. So it skips over the original nitro. And if we have the two para to each other, the new one adds para to the old one, or the original one, then again we have a situation where through resonance we can put that partial positive charge where the original nitro is. Now remember, with toluene, because the methyl group was electron donating, this is a happy thing. In nitration, or with a nitro group, however, if we picture the carbocation next to the nitrogen is electron withdrawing for one, but it also has a partial positive charge. So not only is it more electronegative and pulling electrons away from that carbon, but it's also got a positive formal charge, and of course like charges repel. To put those two positive charges next to each other if we can avoid it. And so if we think about it, then para and ortho are both worse off than meta. And meta would be okay. So by being least worst, then the meta is actually favored, or perhaps disfavored less in this case. That makes a group that does not stabilize a carbocation a meta director. Now, just to summarize what we've talked about so far, the methyl group, by being electron donating, is an ortho para director, and because it enhances the rate of reaction at the positions ortho and para to it, and it actually will also enhance the rate of the meta position. Just not as much. And so what that means is that if we think about the relative rates of reaction, that toluene in any of these electrophilic aromatic substitution reactions, because it has that ortho-para activator, is going to be faster than a ring, just plain benzene, that does not have the activator. In contrast, the meta deactivator, the NO2, by being electron withdrawing, is going to slow down the reaction everywhere on the ring. But a little bit less so at the meta position. And so by being least slow at the meta position, we say it's a meta deactivator. The deactivator part means that our rate of reaction, if we nitrate nitrobenzene, it's going to take longer. We're going to require higher temperatures than nitrating simply benzene alone. So far we have two classes of groups. There is actually a third class, which are ortho-para deactivating, or ortho-para directing but deactivating. So they slow the reaction down, but they still direct ortho and para. And those, for us at least, the only ones we're going to worry about are the halogens. And so if we were to put those in our ordering scheme, they're going to be faster than meta deactivators, but still slower than benzene itself. And we'll look at why that is. To understand the directing effect of a halogen, let's simply consider when we have that carbocation on the same carbon that the halogen is on. The halogen is highly electronegative, so it's electron withdrawing in a sigma sense. So if we think about bond polarity, we're taking electron density out of that carbocation, and that's making it worse. Let's make this a little bigger so it's easier to see. However, we can donate electrons through resonance. And with the halogens, that resonance structure that puts the positive charge on the resonance is not a particularly good one. And so the donating effect, we can say that it's a pi donor. And that electron withdrawing effect we can think of as a sigma, or through bond or inductive effect. So it's a sigma it's pulling electrons away through the sigma bond, but it's donating to the pi system. So because it helps the ortho and para position through resonance, but hurts all the positions, the net effect is it slows them all down, but it slows down ortho and para less, and so it's an ortho-para director, but we'll say that it's deactivating. Now there are actually lots of elements that have lone pairs, so if we consider an oxygen or a nitrogen and how that would affect a carbocation, we'll find that it is electron withdrawing in the sigma sense, but that it is a good pi donor. And they're not those other elements like oxygen and nitrogen and sulfur are not as electronegative, so they're not as electron withdrawing in the sigma sense, but they are very good pi donors, so they do resonance better than the halogens do. And so that acceleration of donating through the pi system is stronger than the sigma effect, and so these are also ortho-para directors and activators. So if we go back to our chart, think about ortho-para directors is going to be any alkyl group that any carbon-containing chain, methyl, ethyl, propyl, cyclohexyl. It will also be any group that has a lone pair. So we could have an oxygen of an alcohol, an oxygen of an ether, an amine, anything along those lines that's electron donating will help activate the ring and activate it more at the ortho and para positions. In contrast, anything that's electron withdrawing, that is, does not have a lone pair and does not have the ability to donate through the pi system, will be a meta deactivator. Now notice if we put a nitrile group on there, we may think that it's more highly substituted because we've added another carbon. But because the nitrogen is an electronegative element, it's pulling electrons out of that carbon. That carbon actually has no electrons to donate to the carbocation, and so it even has a partial positive charge. That's not a good interaction. So a carbonyl, whether it's a ketone or an aldehyde or an ester or an amide, is also going to be in the same situation. You have a pi bond there, but you don't have resonance with it, and so you have no help for the carbocation. So you're not an ortho-para activator, but a meta deactivator. And so in summary, we have two things to consider when we have an original group or something already on a ring. The first is the directing effect, which is where a new group would be added, and that can be either ortho-para or meta. The second thing to consider is how fast a reaction will go, and our substituents, our original groups, can be either activating or deactivating. When we consider the combination, most groups are either ortho-para activators, which stabilize the carbocation, or meta deactivators, which do not stabilize the carbocation. There's a special case, the halogens for us, which are stabilize the carbocation but slow down the reaction, and those are called ortho-para deactivators. And there are no meta activators. If it's favoring the meta position, it's because it's electron withdrawing, and so it's always going to slow down the rate.